All right, now on to calculating ion concentrations within a particular solution stoich problem. So here's another example. We've got two substances, ammonium oxide mixing with cobalt-3 chloride solutions, and the question asks us what mass of solid product is produced, but it also asks us to determine the concentration of oxide and ammonium ions in the supernatant. Now, supernatant refers to the liquid on top of the solid. So this is unreacted ions floating around free. So, step one here is the same as per usual. We need a balanced chemical equation to allow us to determine what the heck that solid product is anyway. So we have ammonium oxide reacting with cobalt chloride, make ammonium chloride and cobalt oxide. Let's balance that. Let me see. We're going to need 2 of these, and 3 of these means I need 6 of these. Cool. Who the heck is our solid product that they're asking me about? Ammoniums, anything with an ammonium, soluble. Metal and a halogen, soluble. Ammonium, soluble. Oxide, there it is, insoluble. Let's go ahead and write the net ionic equation here just for good practice. Remember, anything with an AQ behind it is going to get split into its ion pieces. So 6. So 3 sets of 2, NH4 plus, 3 oxides. We got 2 cobalts and 6 chlorides. Here's another AQ, 6 ammoniums, 6 chlorides, and then my cobalt oxide, which I cannot break apart. This is the complete ionic equation. Anything that does not change gets crossed out. Excuse me. And only the ions pertaining to our solid will remain. So ammonium does not change. It's located on both sides in identical form. Same with the chloride, leaving only my 3 oxide ions, 2 cobalt ions, together yielding my cobalt oxide solid. So this will play a big role when we come back and try to figure out the concentrations of our ions. So to find our amount of solid product, we're going to follow the same solution stoich procedure that we did in the last video. So starting with our first reagent here, since they don't give me a mass to start off my map, they give me a volume. We're going to have to start with that volume. Milliliters, not so good, so we're going to jump to liters. Regardless of what unit they give you for your starting unit in these types of problems, the first thing we've got to do is get it to moles. So we're going to use this molarity feature here. Molarity is moles per liter, and that's what's going to allow us to convert right off the bat here to moles of ammonium oxide. From there, we've got to go to moles of product, our solid product, and it asks us for the mass, so the last step is 2 grams. So 4 arrows, 4 conversion factors. The first one, going from milliliters to liters, that's a pretty easy one. Milli means 1,000th. So 1 milliliter is 1/1000th of a liter. Arrow number 2 here is where our molarity comes into play. Molarity is a ready-made conversion factor between moles and liters. Arrow 3 here comes from our balanced chemical equation, the coefficients. So there's a 3 in front of our ammonium oxide and a 1 in front of our cobalt oxide. Last arrow is going to be to convert from grams to moles. So that requires the formula mass. Let me grab my periodic table here. So I've got 2 cobalts and 3 oxygens. Gives me a formula mass of 165.86 grams cobalt oxide. All right, all of my conversion factors are ready. Let's set up our boxes. Here we go. Problem started us off with 25 mils. Off we go. 1,000 milliliters. 1 liter. Check. 1 liter. 2.5 moles. Check. 3 moles. Remember to follow your conversion factors. Whatever number is next to a unit in your conversion factors, the same must be true in your boxes down here. Marvelous. Multiply all the way across the top, divided by all the way across the bottom. That gives us 3.455 grams of our solid, but I don't know yet if that's the answer. We got to do this whole thing again for this second reactant here. Can you see that? Yes, you can. So once again, they started us in milliliters. 30 milliliters of that substance. Milliliters, not good enough, to liters. And then we'll go to moles of that cobalt chloride. Then we're going to our same product as before. 4 arrows, 4 conversion factors. First one, nice and easy. Milliliters, 2 liters. Though if metric units are difficult for you, I suppose that one is not nice and easy. Back to our problem to get our moles to liters conversion. In this case, it was, 2 moles per 1 liter of our cobalt chloride. It's a lovely pink color, cobalt chloride is, just in case you care. Step 3, moles of reactant to moles of product. We go to our balanced equation. There's a coefficient of a 2, if you remember, in front of our cobalt chloride, and a 1 in front of our cobalt oxide. Step 4 is that formula mass once again. I may have to break this into 2 videos. This may be too long. Okay, so they started us off with 30 milliliters of that. Cross out your conversion factors as you go. Keeps you honest. Makes sure you don't forget anything or mix up numbers or some such. There's that one. All I'm doing is matching up the units catty corner. Because when something is catty corner, we can cancel it, and we like that. Okay, multiply all the way across the... Whoops, I dropped my calculator. Divided by 2,000. So, as you notice, that 3.455 did in fact turn out to be my lower number. So this is the one that actually happens. This one does not. So my limiting reagent is the reagent that gave me this number, my ammonium oxide. So we have completed the first part of this problem. We have found out the mass of solid product produced. But if you remember the problem, that was only part of the request. Now it asks us to determine the concentration of oxide and ammonium in the supernatant. So the liquid on top of this solid that we just calculated, there's going to be some free-floating ions. All of these guys. Now, the cobalt and the oxide combine together to make our solid. So our concentration of our oxide has in fact changed because my oxide is going into making my solid. However, notice my concentration of ammonium does not change. So let's go ahead and do that first. All right, so let me rewrite my complete net ionic over here. Actually, no, I'm not. I did it at the beginning. I forgot I made that a separate step. So once again, ammonium did not change. So that means the amount of ammonium ion in this here is the same amount of ammonium that I ended with. Since it asks for concentration of ions, the concentration they want is molarity. This means I need moles of my ion per liter of solution. Since this is per liter of solution, it should be noted that this is total solution, since we have in fact mixed our two solutions. So we had 25 milliliters, and we added that with 30 milliliters. So 25 plus 30 is 55. 55 divided by 1,000 is 0.055 liters. Now I need that moles piece, though. How many moles of ammonium were present? Well, if you remember, the problem told us that we had 25 milliliters of a 2.5 molar ammonium oxide solution. So let's figure out just how much ammonium there is in this. So we're going to start off pretty much the same way that we did with the solution stoich, because we got to get to moles, from milliliters to moles, and we're just going to use whatever conversion factors we need to get there. Well, milliliters never did me any good, so we're going to first convert from milliliters to liters. Well, I don't want liters either, I want moles. Remember, this molarity is a ready-made conversion factor from liters to moles, but remember, that pertains to ammonium oxide, not to ammonium ion. We are looking at ions now, not compounds. So if you look at this formula, I hope you notice that there are 2 ammoniums per every 1 mole of that ammonium oxide. For every one of these molecules, we get 2 of those ammoniums. So all of that should cancel out everything except that ammonium ion that I was looking for. So 25 times 0.25 times 2, whole shebang, divided by 1,000. So I have 0.125 moles of ammonium ion in my 25 mils of that 2.5 solution. Well, there's my moles. Here's my liters. Let's figure out that concentration. So 2.27 molar solution of ammonium ion. That number unit thing still applies. The question also asked us about oxide, but let's pause and think about the oxide for just a moment. Back to our net ionic equation up here, notice my concentration of oxide in the before situation and the after situation is going to change because my oxide is present in my net ionic equation. It's actually doing something. It's becoming this solid here. But we found out in our solution stoich that our ammonium oxide is actually the substance that runs out. So, ammonium oxide is the reagent that gave me this amount of cobalt oxide, but what ion do these two have in common? The ammonium oxide provided the oxide in my cobalt-3 oxide. This means that we had to run out of these oxide ions in order to stop production of my cobalt here. The ammonium doesn't play any role. We saw that in the net ionic equation up here. Look, the ammonium did not change. The oxide, however, did, and that is the ion that runs out first in order to stop production of cobalt oxide. So there's actually no concentration calculation that we need to do because my oxide runs out. There is none left. There might be a negligible amount left if you take into account KSP, but that won't come up until the equilibrium chapter. So don't fret your pretty head about that just yet. So since this is the ion that ran out, we have none left. So that is our first problem dealing with calculations of ion concentrations. I will put up another one shortly thereafter, but for now I am out of time. Best of luck.